Hi everybody. So now I'm going to continue these examples for solving problems involving instantaneous rate of change. So we're going to start with example 2, and this function is a quadratic, something we're used to dealing with, but I'm going to show you a different way of actually solving this problem that is going to be a little bit advanced. So remember, you can solve this problem in the exact same way that we already learned, where you're just going through that algorithm of finding the rate of change right before and right after, seeing averages to zero, etc. But I'm going to show you something a little bit different that's a little bit more advanced. This is of particular interest for those who are taking calculus next semester. So note right away that we're looking for a minimum at -2. And using our knowledge of quadratics, we can do the x value of the vertex is minus b over 2a. So -4 over 2 times 1, which is -2. And we see that this is the a value is positive. So this opens up. So we do know that this is going to be a minimum, but we need to show that using our new methods. So let's recall that the average rate of change is just delta f over delta x, which means the change in f over the change in x. Okay, so when we do this a plus h, where in this case a is going to be 2, minus f at a, all over h. So that's our difference quotient, okay, formula, which is just slope rearranged and simplified on the denominator. Okay, so in this case, we're going to let a be equal to 2. Don't be confused with this a up here. That's just the a value. Here we're talking about a specific x. So we're looking at a equals -2 because that's the point that we're checking. Okay, so f at a plus h is, we're just going to find then f at -2 plus h. Okay, so f at -2 plus h, we're just going to put in a -2 plus h every time we see an x. So this is our first section here. So -2 plus h all squared plus 4 times -2 plus h minus 21. Okay, so that is f at -2 plus h. Then we're going to subtract f at -2. So that's just -2 squared plus 4 times -2 minus 21. Okay, so that is f at -2. So we need to expand this. So -2 plus h all squared, you might need to do that on the side if you're not able to figure that out on your own. Okay, -2 plus h all squared, that's not just 4 plus h squared, right? We have to actually expand the binomial. So that gives us, if you want to rewrite that even as h minus 2 times h minus 2, okay, I just rearranged this. You get h squared minus 2h minus another 2h, so minus 4h plus 4. Okay, so I just changed the order from -2 plus h to h minus 2 and squared it. Okay, so this is what you get from this. Okay, so we'll go back here. So we get, in our first bracket, h squared minus 4h plus 4. Okay, that is that expanded. Okay, now we expand this 4 times -2 plus h, so that's, that's not a plus, that's a minus 8 plus 4h. So -8 plus 4h, that's just this being expanded. And then minus 21. Minus, oh, here I'm getting a call. Just a minute, I'm going to have to pause this video. Actually, I'm just going to have to answer him later. Okay, so when you figure this out, -2 squared plus 4 times -2 minus 21, you get, sorry about that, you get -25. Okay, sorry about that. Okay, so now we want to simplify what's in this bracket. So the h squared, there's only one h squared, minus the 4h plus the 4h. Notice those cross off, so I'll use different colors. So the minus the 4h plus the 4h, those cross off. And notice I get, so then plus 4 minus 8 minus 21 gives me minus 25. So that's the first bracket. And then this becomes just plus 25. Okay, so now I have just h squared. And all along, these were all divided by h, okay? So this is just divided by h, this whole thing. This was just divided by h. This whole thing is just divided by h. So now we have h squared divided by h, okay? Because this up here was just the a plus h minus the f at a. Again, all divided by h. I'll be honest, I forgot to write that over h. So each of these should be divided by h to remember this part, okay? So now we're left with, what does this mean? Well, we can simplify this to h squared divided by h is just h. So what have we done here? Well, what we were finding was the slope of the tangent. This formula represents the slope of a tangent, okay? Or the slope, sorry, between any 2 points, where a plus h and a are the 2 points. Now, a is the point we wanted, -2, and h is some number very, very small, okay, as close to 0 as possible. So ideally, to find the slope of the tangent, what would h be if we could make it that way? Ideally, h would be equal to 0, right? Ideally, h equals 0, right? Because we want the slope at that exact point, so 0 away from a. But the reason why we can't do that here is because we can't divide by 0. But now we're left with this expression, which doesn't divide by h anymore. So therefore, we can actually let h be equal to 0. Okay, so we can actually make that h as small as we want. So we can actually make it 0 now because we don't have this nasty division anymore. So therefore, we know that the slope of the tangent at that point is exactly 0. So this is the first time that this is actually not an estimation. This is the exact answer. Okay, this is the exact thing, that the slope is exactly 0 at this point. So I'm going to write a little sentence here so when you're studying you can remember what we said. So therefore m equals h, and we want h to be as small as possible. As small as possible, ideally 0. Before h was the denominator, the short form there, so h could not equal 0. So h could not equal 0. And then if you need to write because you can't divide by 0, you can. But now, setting h equal to 0 does not result in division by 0. Therefore, m equals h equals 0. And we're happy. So that verifies that we have a horizontal tangent or a high point or a low point. So to check that it is in fact a low point, so verify that it's a low point, we can actually just put in numbers into the function. So we can check f at minus 2.1 and f at minus 2 and f at minus 1.9. So notice these aren't the slopes of the tangent before and after. These are just the coordinates before and after to determine that minus 2 is lower than both minus 2.1 and minus 1.9. So minus 2, we already figured out up there, was minus 25. If you run minus 2.1 through, you get minus 24.99, and the same thing here. Okay, so these aren't the slopes, these are the actual coordinates. So that's saying that at negative 2, we're at minus 25, but just before and just after, these coordinates are just slightly higher at minus 24.99 and minus 24.99. So that means that it is in fact a minimum. So that's a more advanced algebraic way of showing that something is in fact a minimum or maximum. So this method right now can only be used with quadratics. I'm not actually requiring that you are able to do this exact method for the test, but it is something, if you're going into calculus, that you should understand, and it does kind of strengthen and deepen your understanding of what it is you're actually doing, rather than just memorizing a list of steps and doing it. This is kind of showing an understanding of what is actually happening. Okay, so if that kind of freaked you out, now we'll just do a more straightforward example that's just similar to what we did yesterday with a cubic function. Okay, so this is a cubic function. Okay, it's cubic because its degree is 3. So we're learning all about these next chapter. So we want to know if there's a maximum, a minimum, or neither at x equals -1 using the difference quotient, and then it wants some justification. Okay, so I actually graphed this on, what's it called? Did I write underneath my screen again? I will not be happy if that happened, and I apologize if it did. Okay, here is a sketch of what this function looks like. So I just used GeoGebra because I know you guys aren't used to cubics yet, to kind of show what this guy looks like. So he comes up, does a little dipperoo, and then goes off to infinity again. So at -1, we can see that it does appear to be at a local maximum. So notice it's not the maximum of the whole function, like the function continues up and has higher points, but this is something called a local maximum, because at in this area, that is a turning point. Okay, so we want to see, or we want to show that this is in fact a maximum using rates of change. So we're going to need to do a little bit of work, as per usual, to do this. Okay, so we start with our before. So we're going to do the rate of change before -1. So think before -1 in this case is going to be, we're going to use an h by the way of 0.1 is what I chose here. And our before is actually from -1.1 to -1. Okay, in that direction. Because if you're looking left to right, -1.1 comes before -1. So -1 is a larger number than -1.1. So our slope then is f in this case, f at -1 minus f at -1.1, all divided by 0.1. Okay, because remember, -1 is over here, so you want to do the right one minus the left one, the right one minus the left one. So if you put -1 into the function, you get -5. And if you put -1.1 into the function, you get -5.01. Okay, divided by 0.1. So I'm going to show you on GeoGebra, you can actually do this to save yourself some time. You can actually just search f at -1, enter, and it'll give you the value. And f at -1.1, and it will give you the value. So obviously you can't do that on a test, but in your homework or on an assignment, you can do that. Okay, so when you do this, you get 0.1. So that means that the slope of the tangent right here, right before this, is positive 0.1. So that matches the graph because it's going up, so that makes sense that the slope of the tangent there is positive. So now we want to do the after. So that's from -1 to -0.9. Sorry, 9, because think about it, you're looking left to right. So -0.9 is actually bigger than -1. So your slope then is going to be f at -0.9 minus f at -1 divided by 0.1. Okay, you put that in, you get -5.1, minus -5 divided by 0.1, and that gives you -0.1. So again, that matches our graph. Just after this, it's a slightly sloping down tangent, so that makes sense. So this means that, notice they average to 0. And notice that this is positive, so it's sloping up. This is negative, so it's sloping down, so it makes sense that it would be a maximum. So now you have to have your nice little concluding sentence, okay? So therefore, since, okay, the slopes average to 0, actually I should say the slopes of tangents on either side average to 0, and before is positive, after is negative. Therefore, x equals -1 is a local maximum. All right, so there we go. I followed all these steps. So again, these are the steps here. So did I do them? Yeah, I did before and after. I found the average. I analyzed the rates of change before and after, that it went from positive to negative, and I wrote a concluding sentence. So I'm done. Okay, last example is example 4. This is kind of a different type of question about some bacteria. So Tim has 25 bacteria growing at 15% per hour. He observes the culture for 12 hours. Over this time, when is the instantaneous rate of change the greatest? Well, this actually doesn't really require any calculations from you. It just requires an understanding of exponential functions as well as what the rate of change is. So you don't actually have to do any calculations here, really. So first we'll say let B at T represent number of bacteria after T hours. Okay, so if we remember from last year, we have B at T equals 25, because that's our initial population, times 1.151 plus our rate of growth to the power T. Okay, so if we were to draw a rough sketch of this, we would only need this quadrant because time, in this case, would only start at 0, and we would only need to get up to 12 hours, and then it would stop. So it would start here at 25, and it would go increasing until it hit 12. So because we know that the instantaneous rate of change is represented by the slope of the tangent, we can just think about what's happening to the slopes of the tangents. Well, here they're positive, and they continue to be positive throughout this entire span. Okay, so as the bacteria grows, the slope of the tangent would be positive the entire time, and the slope of the tangent would increase as this curve gets steeper and steeper. So therefore, it would actually be at its steepest, which is the same thing as saying that the instantaneous rate of change is the greatest at T equals 12, so the very top part. Okay, so you need to show your understanding that greatest instantaneous rate of change is equal to the steepest slope of tangent. Okay, so you need to tell me that somehow in your sentence. That's what I'd be looking for, this connection of this graphical understanding. Having a sketch here, maybe making it a little bit more accurate would be nice. And just discussing that because it's exponential growth, it's growing, 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 so therefore it will be at its steepest at t equals 12. So I'd be looking for a nice sentence showing your understanding of this, connecting your understanding of an exponential function, and then the conclusion that t equals 12 is when the instantaneous rate of change is the greatest. Okay, so if you have any more questions about this stuff, I really hope you ask me in class tomorrow. I hope I didn't write above my head. I kind of was forgetting about that. I will practice more. But thanks so much for watching, guys. And of course, I really hope that you learned a lot.